So welcome, this is 48H video 2 and we're going to continue our study of circular motion, and in particular at the moment we're looking at uniform circular motion, which means constant velocity or constant speed circular motion. And here we have a view looking down on the circular motion, and we see that there's a mass going in a circle and it has a constant speed, so it means it's uniform circular motion. There's a centripetal acceleration pointing towards the middle of the circle. As we said last time, if you don't have that centripetal acceleration to change your direction, you don't go in a circle, you go in a straight line. So we need a centripetal acceleration, and that centripetal acceleration will be paid for by another force, some kind of force that already exists in the system. And often it's tension in a string, or it could be a gravitational pull from a planet, it could be a frictional force of tires, it could be a component of a normal force on a bank track, but there'll be some existing force which pays for that centripetal acceleration. What we say is, consider a ball of mass m tethered to a string of length r. So in this case is a string connecting the middle point of the circle to the mass. The ball travels in a circle with speed v. The ball experiences centripetal acceleration that points towards the center of the circle, and this acceleration is caused by the tension force provided by the string. Well, what do I know? I know that the centripetal acceleration is always the speed squared over the radius, so I know the size of the centripetal acceleration that I need. And I know that Newton's law applies along that radial line, in line with the centripetal acceleration, and I know that the sum of the forces along the line where the acceleration points is equal to ma. Now here's a tip. It's better if you always draw the diagram from the side. So now I'm looking from the side and I see my mass, and then my centripetal acceleration points in a positive direction because the mass is at the left hand side of the diagram. And the advantage of that is that you don't inadvertently introduce negative signs because you happen to draw the mass at the right hand side of the diagram. If I draw the mass at the right hand side of the diagram, I have a negative AC and I have negative tensions, and you might remember one of them but not the other. So my habit is I always draw the mass on the left hand side of the diagram, and I have the tension force, I have the centripetal acceleration, I have my radius, I have my mass, and I will have, it's hard to draw, but I'll have my speed. So we play games with these. There's 4 classic examples. There's a mass on a string going round a horizontal circle. Maybe it's on a smooth frictionless table. There's a car going round a circular level track. There's a mass on a string going round a horizontal circle, but this time the string is not horizontal. It dangles as if it's what's called a conical pendulum. There's a certain angle between the string and the vertical axis. And then we have the car on a banked track. In each of these cases we have some force that is paying for the centripetal acceleration. We have the tension for the mass on a string going in a horizontal circle. We have the frictional force of the tires on the road for the car going around a horizontal track. We have the component of tension. This is going to be a tension component for the so-called conical pendulum, because the tension is not in line with the centripetal acceleration. So it's the component of tension which is in line with the centripetal acceleration. And for the banked racetrack, we have the component of the normal force, which is in line with the centripetal acceleration. So for the top two diagrams, we have forces that we can find or whatever that are in line with the centripetal acceleration. And in the bottom two diagrams, we have forces that are not directly in line with the centripetal acceleration, but which can provide components which are in line with the centripetal acceleration. So let's do some examples of these. So we say a 2 kilogram ball is attached to the end of a 4 meter long rope. So here we have 2 kilograms and we have 4 meters, and there's the middle point of my circular motion. The ball moves in the horizontal plane. The string can withstand a tension, is my tension. So T max is equal to 80 newtons. Beyond 80 newtons, the string will break. What is the maximum speed the ball can attain before the string breaks? So here's my speed, my V. Let's have a look. I have a centripetal acceleration. I didn't draw that in, but I know it exists, so I have my AC. I suppose I have a weight, and I have a normal force. This is Fn. This is Fg. That's about it. So as I did previously with Newton's second law, when there's an acceleration, I will resolve my forces along the line of the acceleration. So I say the sum of the forces horizontally is equal to ma. Well, I know that ma is m centripetal acceleration, and I know that my centripetal acceleration is v squared over r. So I get the sum of the forces horizontally is equal to m v squared over r. So I look at my diagram, and although I have a weight, it's at 90 degrees to the horizontal, and although I have a normal force, it's at 90 degrees to the horizontal. So the only force that's in line, or has a component in line with this direction, is the tension. And I say plus T is equal to my mass, which is 2. Plus T is equal to m v squared over r. Now what do I know? Oh, I know that for the condition being considered, the maximum speed, I have the maximum acceleration, I have the maximum tension. So I say the maximum that this tension can be is 80, plus 80, points to the right, and this equals the mass, which is 2, times v squared, which is what I want, over the radius, which is 4. So v squared is going to equal 4 times 80 over 2. Remember, let the paper do the thinking. That's going to be 160. So v is equal to the square root of 160, which is, just so we remind ourselves, it's not 40. Let me get my calculator. So I say second square root 160. So this is going to be 12.6. So this equals 12.6 meters per second. 12.65 I've got down. Yep, 12.65 it is. So there we have it. I started off as usual with a clear diagram showing all the forces and the accelerations and the masses and the velocities. And then I picked a direction to apply Newton's laws. I picked the direction along the line of the acceleration and said the sum of the forces equals ma. I then substituted in what I knew and found what I didn't know. Cool. let's look at this next diagram. In this next diagram, we have a racetrack. It says a 6 kilogram car. So let's draw a 6 kilogram car. Is moving on a flat horizontal track that makes a turn of radius 2 meters. So this radius here is 2 meters. There's a 0.8 mu static equals 0.8. So that tells me there's a frictional force that I may need to take into account. It's between the tires and the track. What is the maximum speed the car can have while making it around the track? So V. Let's have a look. What else do I know? Well, I know, of course, I'm going in a circle, so there must be a centripetal acceleration. And of course, I know there's a frictional force, and the frictional force points towards the middle of the track. I have a Fg, and I know that value is going to be 60 newtons, and I have an Fn, and that equals 60 newtons because I'm on a horizontal track. And then I say, okay, let's try and solve this. So I say, okay, I'm going to resolve my forces in line with the centripetal acceleration, and I say the sum of the forces horizontally is equal to ma, which equals, well, it's going to be a centripetal acceleration, so it's mac, which equals m, and centripetal acceleration is v squared over r. So the same beginning. Now I look at my diagram, and again, this weight is perpendicular to the direction of applying Newton's laws, so I can ignore it. It's got no component horizontally, and this normal force is perpendicular to the direction I'm applying Newton's laws, so I can ignore that because it has no component. And so the only force I have is this Ff, which is pointing to the right. So I can say Ff is equal to my mass times v squared over r. Let's substitute in what we know. Oh, we don't know Ff. So I have to say Ff is equal to 6 times v squared over 2. Well, I have one equation, but I have two unknowns. I've got to be able to find this Ff, and so I do a second part. I can show it like that, and I say, well, what do I know that would include Ff? Or alternatively, I can say, well, let's say, what do I know that would include Ff? And I say, oh, Ff is equal to mu static, or it's less than or equal to mu static times Fn. But here, what is the maximum speed? Means that I'm driving this race car until it's on the point of slipping, when static friction of rolling gives way to the kinetic friction of sliding. When you drive your car normally, your tires press down on the road. They roll. They don't scrape along the surface of the road. So the appropriate friction for driving is static friction. And if you drive too fast or brake too hard or go around a corner that's too tight, you will stop rolling and you will start sliding. And that's when you leave those tracks on the road. You're leaving tire on the road. Well, we're at that maximum point where we go from static friction to kinetic friction, and so I say at that point Ff is equal to mu s times Fn. Oh, well, Ff is equal to 0.8. We had that before, given. And Fn, well, Fn is, by observation, I can say it's 60. So Ff is equal to 48 newtons. I can substitute back in. 48 is equal to 6 over 2 v squared. So v squared is equal to 48 times 2 over 6. And again, try and avoid doing things in your head. This is going to be 48 over 3, which is 16. So v is equal to the square root of 16, which is 4 meters per second. Now, plus or minus 4 meters per second, I suppose, but this is a speed, which is a scalar, and so we've used the positive answer on that. So there's a second example. Again, I drew a detailed diagram. I looked for my centripetal acceleration. I resolved my forces along that line. I used Newton's second law, the sum of the forces equals ma. I recognized the A was a centripetal acceleration, and I used the equation to get the centripetal acceleration. I then substituted in and found, oh, I don't know my frictional force. I used Ff is less than or equal to mu s times Fn, substituted in, got my answer. Let's just stop for a minute and think. This is a one-step problem. Let's do this in a different color so you can see it. This is a one-step problem. Well, it's a two-step problem because I used that equation. Well, it's a three-step problem because I used that equation. And actually, I actually invoked Newton's first law vertically to get that value there. So in effect, this is a four-step problem. This is quite a sophisticated problem. So yeah, we treat it with respect. So let's look at this next problem. So now we come on to a series of problems where they're a little bit more involved because they have some trigonometry, and a good diagram really helps. So again, draw your mass over to the left hand side, and let's picture this. So we have a conical pendulum, and this ball is going in a circle. It says a 6 kilogram ball is attached to the end of a long string. The ball revolves at constant speed of 3 meters per second, so my V is equal to 3 meters per second in a 4 meter radius, 4 meter radius horizontal circle that forms a conical pendulum. And then it says find the angle that the string makes to the horizontal. Oh, it's this angle here. It's that angle there. Again, let's add things that are not mentioned. There's a centripetal acceleration which points towards the middle of the circle, not along the string. The acceleration points towards the middle of the circle. We have a weight which is 60 newtons. There's my Fg. There is no normal force. Normal forces only occur when one object is resting on another object. And this ball is not resting on anything. It's been pulled up by a tension force, which is not mentioned, but a tension force in this string. So there is no normal force in this case. And that's about it. I can't think of any more forces, and so I should be able to make a start. And so I come along and I say, the sum of the forces, I'm going to use the horizontal line because that's where my acceleration points horizontally, is equal to ma, which equals, well, it's centripetal acceleration, so it's mac. Well, I know the value of AC, so it's mv squared over r. And now let's try and put some forces in. Oh, my 60 Newton weight is perpendicular to the direction of interest, so that has no component. But my my tension does. So my tension, please forgive the crowdedness of this diagram, the tension component is equal to T cosine theta. And I hope you're getting to the stage where that's not a stumbling block for you. So you can look at the diagram and you can recognize whether it's a cosine or a sine of the angle. Remember, I want one side, I'm using the other side, and I'm making use of the angle in between. It's a cosine of the angle. Also remember, the original vector is always the hypotenuse. So draw your triangle. Don't skip on it. Draw your triangle. After 30 years, I'm drawing the triangle because it makes it easier. So draw the triangle. So then I say, okay, so plus T cosine theta is equal to m v squared over r. Okay, so let's substitute in what I know. So plus, well, I actually don't know t, so let's leave that. And I actually don't know cosine theta, so let's leave that. Is equal to m 6 v, which is 3 squared, over the radius, which is 4. Well, okay, that's 6 times 9 over 4, which is 1.5 times 9, which is 13.5. Okay. Problem. I have two unknowns. I have theta, which I'm trying to find, but I have this tension, which I don't know. So I need to make it into a two-step problem. Find t using, well, if all else fails and you've tried using Newton's second law horizontally, then you can try using Newton's first law vertically, because that plane has no component of acceleration. So I'm going to say the sum of the forces vertically equals 0. So let's change colors so I can see this work a bit more clearly. And I'm going to say, well, I have this weight is in this vertical plane. So there's my 60 newtons. And of course I have a component of the tension in this vertical plane, and this is going to be T sine theta. Again, I hope that's not going to be the limiting factor for you. And I say, well, plus T sine theta added to minus 60 is equal to 0. So T sine theta is equal to 60. So now in principle I have two equations and two unknowns. I can simply isolate t and substitute in. So let's just do that. It's the simplest way. So I simply say, okay, so I can say t cos, oops, a daisy, well, 60 over sine theta is my t from here, times cosine theta is equal to 13.5. So cosine theta is going to be adjacent over hypotenuse, and sine theta is going to be opposite over hypotenuse. So, oh yeah, okay, this is 1 over tangent theta, because it's adjacent over opposite, is equal to 13.5 over 60. So that gives me, I'm running out of space, that gives me tan theta is equal to 60 over 13.5. So theta is equal to tan to the minus 1 of 60 over 13.5, which equals, get my calculator. The first thing I always do when I'm dealing with trig is I check I'm in degrees, if I want to be in degrees, and I go second tangent, and it's going to be 60 divided by 13.5, enter, and I get 77.3 degrees. So this equals 77.3 degrees. Cool. There we have it. So let's just review our approach. We drew a good diagram as usual. We resolved our forces in line with the centripetal acceleration as usual. We substituted in what we could find. In this case, we found we had two unknowns in this equation, and so we needed a second approach. I decided to say the sum of the forces vertically equals 0 because there's no acceleration vertically, and found another equation that contained t and theta. Two equations, two unknowns I can solve. So it's longer, it includes trig, but it's the same basic approach. Last example that we're going to look at in these four. So what we have here is we have a race car moving around a horizontal track. Now, I need to draw this out because it's only just recently I realized that some students have a different view than what I expected. So think of it as being like a funnel, and the race car is driving around the edge of the funnel. So the race car is going round. So if I draw this thing from the side, I have the race car on the edge, and we have the middle there, and it's going round and round and round and round. Okay. So it says a 4 kilogram car is on a banked circular track. So 4, and then this is the circular track. And what we're going to find is the car has a radius of 5 meters. So this is 5 meters radius. The banking is designed so the car does not rely upon static friction when traveling at optimum speed. And there's some roads are engineered like this. If you're on an interstate, sometimes you'll find you go around a corner and you didn't even touch the steering wheel. You notice it more when the corner is tighter, so you tend to notice it more on actually some local roads. There are a few local roads where for some reason they just banked the road so that you don't actually have to turn your wheel and make the car go in a circle. It actually just goes around because of the banking. So those roads do not kind of put strain on your tires because it's the component of the normal force which points to the center of the circle. So the banking is designed so the car does not rely upon static friction when traveling at optimum speed. If the track makes an angle of 20 degrees, so let's just do this. So this is 20 degrees to the horizontal. What is the optimum speed? So here's my optimum speed, my V, going around in a circle. Let's complete our diagram. Well, clearly we have weight, which is 40, so Fg equals 40, and clearly I have a normal force which equals not 40. I don't know my normal force. I can't use observation for this one because I'm not on a horizontal surface. I have a centripetal acceleration, AC, and that's about it. Again, as I usually do, I'm going to resolve my forces in line with the acceleration. So I say the sum of the forces horizontally is equal to ma, and it's centripetal acceleration, so it's mac, and I know the value of centripetal acceleration, which is mv squared over r. So now I have to try and fill in what I know. and this weight is 90 degrees to the direction of the acceleration. It's the direction of my axis that I'm looking at, so it has no component. And so again, I'm looking at the component, this time the component of the normal force, and this component is Fn. Now, I got some angle issues here. If this angle here, if the small angle is 20, the big angle is 70. If I transfer this up, I can just see that the small angle here is 20. So this would be Fn sine 20. So there's a trick here, and that is you've got to be comfortable propagating your angles, and it really helps if you draw your diagram so that you have a big angle and a small angle. Don't draw your slopes at 45 degrees because you can't tell which is which. So small angle, and other corner of the triangle gives me a big angle. Look at the triangle we're interested in as far as the components. There's a small angle and a big angle. The small angle must be 20 degrees. Okay, so I know that this component, this horizontal component, is Fn sine 20 degrees. And I say, well, Fn sine 20 is equal to my mass, which is 4, my velocity, which is 5, and I've got to square that over my radius. My radius is 5. Let's look. Let me just double check on this. What is the optimum speed? Oh yeah, my diagram's not so good. Can you see how I looked at 5 meters and I drew the line next to it, so I just as I glanced saw that as 5 meters. So caught it though, didn't I? Because I write things down. So that's going to be v squared. Let's rearrange. So we can say v squared is equal to Fn sine 20 times 5 over 4. Okay. Sine 20 is just a fractional number between 0 and 1. And so we have two unknowns though. We have v and we have Fn. So I need a way to find Fn. So I say let's find Fn using, well, I'm going to go vertical again. The sum of the forces vertically equals 0. Again, I need this vertical component. This will be Fn cosine theta. I say plus Fn cosine theta added to minus 40 is equal to 0. I actually know it's cosine 20, so I can say plus Fn cosine 20 is equal to 40. So Fn is equal to 40 over cosine 20, which equals, get my calculator, 40 divided by cosine 20, and that equals 42.57. 42.57. I'm going to use a few decimal places because I don't want to round too much when I'm putting this into another calculation. I say v squared is equal to 42.57 sine 20 times 5 over 4, and that's just math. So I go 42.57 times sine 20 equals times 5 equals divided by 4 equals, and I'm going to get 18.2. So V is equal to the square root of 18.20. V is equal to second square root, second answer. It's going to be 4.26, 4.27 meters per second. And there it is, yeah. So a little bit longer, more use of trigonometry. There's an issue about the angle, and it resolves itself if you draw the diagram more carefully probably than I did. So let's just look at that for a second. So the issue is I have two triangles that I'm thinking about. The first triangle is the slope of the racetrack, and that's 20 degrees. And if that's 20 degrees, I can say that's 70 degrees to the vertical. And if that's 70 degrees to the vertical, I can say that's 20 degrees to the horizontal. Now, we know that the normal force is 90 degrees to the slope. So again, if this is 20 degrees to the horizontal, this must be 70 degrees. And if this is 70 degrees, because this is another right triangle, this must be 20 degrees. But can you see that if you recognize that that's the small angle, and you look at the triangle, and you recognize it's a similar triangle, you can see that's the small angle, so 20 becomes 20. It just makes life much easier if you can recognize that. So I resolve my forces in line with the centripetal acceleration. I tried to solve in one step. I couldn't. I resolved my forces perpendicular to the acceleration using the sum of the forces equals 0. I determined what I needed to determine, and then I substitute in. So again, it's actually a standard problem, just looks a bit more complicated because it's using trig and you've got to know a bit of geometry. So there we have it.